Hello everybody, you're very welcome into this video, the 10th and what surely must be the shortest video so far in this series. Last night, as it happened, in the last video, video number 9, we set up additional design points for different angles of attack, and we ran the solver for angles of attack of 2, 3, 4, 5 and 6 degrees, and given the length of time that it takes to run these solvers, each one running up to a maximum that I have set of 500 iterations. It could have took a reasonable amount of time to complete. So that's it. I let it do its thing and way to bed. So it is now the morning after the night before. And here we are. I have come downstairs to see the table completed with no errors, a couple of warnings there. However, them warnings did come in at 2:15 in the morning, which incidentally is not that long after I started the solver. So it's now 8:30. I don't know what time it finished at, but everything seems to have come through pretty good. So, at any rate, it probably was a wise move to let it just run away there in the background. And look, if you're new to CFD, um, I hope it doesn't come as a shock. It's a fairly regular occurrence and normal thing to do. I do it all the time. If you're an old hand at CFD, no shock there, as you say. So let's see what we got. So we ran the same amount of mesh divisions in all divided flow fields for different angles of attack 2, 3, 4, 5, and 6. Velocity didn't change, obviously 29 meters per second is what we left. 29 meters per second we chose because we were shooting for a target Reynolds number of 50,000, so just under 50,000 there, so we could likely speed that up, or what I probably should have done maybe was drop the dynamic viscosity slightly, because I think I take the dynamic viscosity really out of my head. So I obviously overestimated, which resulted in the Reynolds number being somewhat smaller than what it should have been, the target Reynolds number. But however, with such a small difference there, relative difference, our results should be comparable. But yeah, I definitely would want to maybe sharpen that up and tune either my velocity or my dynamic viscosity, or even make my density slightly larger uh, to get the Reynolds number that I want. This is kind of my driving function here, my forcing function as such. Uh, yeah, minimum mesh, my orthogonality, my mesh hasn't changed any with the different angles of attack. All we're doing is just bringing the area in again at a different angle. Say the geometry hasn't moved, so the mesh wouldn't have moved. Mesh elements are the same. The y plus value has changed. Y plus will change there obviously because our friction velocity would have changed with the different angle of attack. Skin friction as well likely would have changed there with the different angles of attack. So there are things that do change with the relationship between the air and the parts of the airfoil, and how the air is interacting with the airfoil that is driven by a different angle of attack. That will affect the maximum Y plus. So I could see for all angles of attack, my Y plus is still within range. It's still below 1 for this SST, K omega supplemented SST turbulence model. The lift force I could see has increased, so the more I tilt my wing, the more it goes up, with the exception of at 5 degrees I seem to have dropped lift force here a wee bit, which there's either something wrong with 4 or 5. It definitely should be increasing up the way. Lift coefficient is dropped there, so either 4 or 5. I'd say there's something has happened, which likely could be that I should have ran out for more iterations. Maybe I hadn't fully iterated. Something to look into. That's definitely a point of concern. The Reynolds number stayed the same. The drag coefficient here as well. So my drag coefficient is here. Yeah, drag coefficient possibly is something. Again, we're looking a little bit of a discrepancy here on the drag coefficients, because we are coming up all the time when we hit until this design point. It'd be great to be able to freeze a pane here. Let me see if I can just drag force at 3. Between 3 and 4, the drag force hasn't gone up hardly at all, which is odd maybe. Then it's popped up very fast in 5, then it's settled back down again in 6. So as I said, something between 4 and 5 degrees, something funny going on here, which will be worth further investigation to have this right. Drag force characteristic mesh size that has obviously changed because my mesh hasn't changed. And then there is finally my pressure coefficient. Pressure coefficient has dropped again here between 4 and 5. So something odd there happening in 4 and 5. So how do we test that? Well, we're going to go back. I would nearly rerun this because this might have just had a blip itself. Typically what I would do, not straight away, but when I run my next study, whatever it may be, which incidentally in this case is going to be a change to the mesh, so we can do the grid convergence index method. Before I run any of them, I'll go back into the solver and maybe up my iteration slightly. And what I'll do is I'll maybe add a convergence condition to be either my lift force or my drag force or pressure output there as well, just to make sure that I have converged to the correct answer. Just put my maximum convergence as way up. But with that said, let's have a look at how it's performed in a more general manner. Pressure output from 2, 3, 4, 5, 6, 0, yep, sorry, 0, 2, 3, 4, 5, and 6. So what I'll do is I'm going to take a scoot into, just instead of flicking between screens and splitting screens, what I'll do is I'll take a shot of my pressure coefficients here. I'm going to stick them into OneNote. Put them over here somewhere because I know what's coming in next to it. And then in Winslow, I have this graph. If you remember, there's lift coefficient. Pressure was on up here. There's my pressure coefficient. Don't forget my pressure coefficient that I pulled in off the table there was my minimum pressure coefficient. Let's keep that one. Alright. See what we got. So I'll swap over to my trusty pen. And this here is this is alpha angle of attack is equal to 0 degrees, is equal to 2 degrees, is equal to 3 degrees, equal to 4 degrees, and it's equal to 5 degrees there. Alright, so let's see if we just get something that'll stick out a color they haven't used. Use this high pink might do it. So 0 degrees we have minus 3.03. So 0 degrees is the blue, minus 3.03. That's the negative. Just eyeballing. This is all just eyeballing. This might just mark these on. Minus 0.3 roughly. I'm going to say this one here isn't up as far as minus 0.6. I'm going to put this one here. Maybe what would you say now? 0.55 roughly. This one here, not just minus 1.1, minus 1. I am gonna go out on a limb and say 1 would be slightly above it. Oh wait. And this one up here, roughly minus 1.5. It's over 1.575, 1.58, just over 1.58 something. Right. So this here again is at 5. I'm going to check down for 5. I'm going to check this one for alpha 3. Check that one there for alpha 2. And of course we know alpha 1's fine. So alpha 1 with broad agreement. At alpha 2, 0.55. With broad agreement there. This one here, 1.08 I have. 1.0 minus 1.05. Broad agreement there. 4 degrees isn't plotted, but 5 degrees is plotted up here. So 5 degrees, 2.302, so I'm a good bit off here. Right. Well, 5 degrees seems to have some sort of an issue here. And again, 5 degrees is tying up with a lot of the issues that I'm seeing. A drop here in the Y plus, and the, I'm going to have that anyway, drop in the lift force, sorry, and the pressure coefficient maybe going or the drag force going too high. Some place to check in there. All right, so look, I'm going to cut the video off on that because I just wanted to show you what the table design points can be used for. And it's brought up a very important thing that I know I now need to look at if I was looking to design for these sorts of angles of attack, that it is broken down somewhat for these angles of attack. Definitely worth an investigation. Maybe the turbulence model isn't good for the higher angles of attack. Maybe the solver, maybe I should have tried a simple X or a simple C and compared it to a simple C against the couple method. I could also, as I said earlier, increase the number of convergence iterations before stopping the solver to give it more time to find its converged location. And finally, what I definitely should do, just for robustness and thoroughness, is to put in pressure output or lift coefficient or indeed drag coefficient in as a convergence condition as well, just to make sure that one of them critical metrics is also met, or all of them. Why not? You can put in all of them there as well. You're not doing the calculations, the computer is, so don't worry about putting in too many convergence conditions. The more, the better. So there are a couple of things there we could look at to include with the next video. We're not going to do this to run this again. Because I think the point has been made what this is for. So you increase a variable, just one variable, don't increase more than one, okay, because that's the worst thing you can do in CFD is change a couple of things, rerun it, then it comes out right, or appears to be right, and you say, right, what was it that made it right? You know, was it this thing that changed or that thing that changed? And you can't pin it down. So you make one change, run it. If it works, that's the change that caused the improvement. If it didn't work, no, we'll put it back to the way it was, make another change. Okay, and mark it. That's it. You have to do one at a time. It has to be completely iterative till you find what's wrong. And that's what I'll do in this. Now, adding in more than one additional metric as part of my convergence condition, that is fine, because I'm not changing anything. I'm just running it longer, and I'm ensuring that the value that I have is a solid final value for that set of solutions across the fluid domain. So thanks very much. 12 and a half minutes, that's a new record for a short video for me anyway. So again, thanks very much for the time, and in the next video we definitely will look at the mesh independent study using the grid convergence index method. Thanks very much. Have a good day.